Hi there, this is Jacob Nash Algebra Lessons, and this is Unit 6, Lesson 6, on operations of radicals. So just like we've had operations of imaginary numbers and rational functions and polynomials and all that, you can still do that with radicals also. So you can add and subtract, you can multiply and divide, and you can simplify. Those are three things. Now, over here as a review, well, maybe not as a review if you never learned it, but over here where I have the A and B thing, A is the index. That's called the index. We talked about that in the last video a little bit, but if there's no number there, which when we take the square root of something like 49, for example, we know that that's square root, so it's really a 2. And then you might think, oh, I thought when nothing's there, that's a 1. Well, if you had just a 1 there, then that would mean that it's the same thing. So that's what that means. And then B is called the radicand. Oh, I'm still an eraser. B is called the radicand that's in there. Okay, this thing's sometimes really stupid. I don't know why it just moved the whole thing over. And then if there was something outside, like right here, if pretend there's C, that would be called a base. And it did it again, but that doesn't matter because I actually do want to go further. So I have rules and steps. This is what I do for each part that we have today. So only like radicals can be combined. Like radicals mean they have the same radicand and index. So for example, well, I don't need to say for example actually because we have examples. So we'll look at that. And here are the steps. You have to see if they're like radicals. If not, you can't combine them. So in some cases, you don't have to do anything. You have to combine the bases like normal. So the bases are the things that are not under the root. And then you don't do anything to the radicands. You don't like add them or something, the numbers that are in there. You just keep that same. You treat it as if it's a variable, kind of. That's not good. Computer sounds like it's going to explode. I have it open nearby. I don't know what that is. Okay, so let's look at an example. So we need to first see, are these like radicals? That means they have the same index and power, or index and radicand. So the index is, since there's no number, you can just know that's a 2. So they do have that. Oh my gosh. Are you kidding me? I don't know why it does this. But it does not have the same base. You see 6x and 5x. That's not the same. And it did it again. This thing is so stupid. Oh, sorry. If you know why it does that, then tell me. Okay, so because they don't have the same radicands, then you cannot combine. So I'll just say this. You can't do that. Okay, let's look at a different one. Hopefully there's one we can. Okay, we have 8 root 2b minus 7 root 2b. So they do have the same index of 2, and they have the same radicand of 2b, so we can combine them. Like I said, you treat the square root of 2b them like they're variables, as if they're x's. So then if you think about that, it would be 8x minus 7x. So you just combine the bases, which would just be x. Well, yeah, and if we said x was square root of 2b, then we'll say that. I don't want to confuse you with that, but just that's basically what you're doing. You're treating it like it's x. So you combine the bases, which are 8 minus 7, which is just 1. So you don't write anything, and you still have the root 2b. So that's the answer for that one. Okay, now we have this one. Are they like radicals? Yes, same index and radicand of square root c. So we have 47. We combine the bases, 47. There's nothing there, so that's an understood 1. So 47 plus 1 is 48. Now don't think that means that you should only do 47 because there's nothing there, because it can't be 0 root c. That's not something that there is. So then we just have root c. So that's the answer for that one. So it's not really that complicated for adding and subtracting. Okay, multiplying, dividing. maybe a little bit more complicated. The rules, you can only multiply and divide if there's like indexes. So the radicands can be different in this case. So this is kind of like fractions to denominators. Disregard that if it doesn't make sense, but basically you can only add and subtract fractions if the denominators are the same, but it doesn't matter if they're the same for multiplying. That's the same for the roots, the radicands. The radicands have to be the same for adding, subtracting, but they can be different for multiplying and dividing. But the indexes still have to be the same. So let's look at examples. Not a lot of room I made here. Okay, so we have the 7th root of 128 times the 6th root of 3. Are the indexes alike? No, 7 and 6, so cannot do anything there. It doesn't matter that the 128 and 3 are different, the 7 and 6 are different. For this one, they do have like indexes. We can see it's cube root, or just third root. And so now we just I didn't say that the steps, but you just multiply, you combine the radicands and bases if there are some. But you might want to simplify. Well, not really might want to, you should. So we have the -8. Well, actually, we see that there's a -8 and a 64. So these actually are simple because we can just already take the cube root of them and they'll come out evenly. Because although in square roots it can't be negative, it can in the cube roots, because if you notice you have -8 times -8 times -8, for example, that does come out to equal a negative number, so that's possible. Okay, so for this one, the cube root of -8 would just be -2, because 3 -2's multiplied by each other equal -8. Okay, then, and that's just something that you would just know. You could put that in a calculator, but that's why I had the last lesson, because that's just a simple one. Alright, this cube root of 64, don't put 8, that's the square root, so you need to do 4. And then you multiply those together, so you get -8. So that's interesting. It actually turned out to be what that was. So that's our answer for that one. Alright, this one, now we have dividing. They do have like indexes of 2, pretty much. Although, I know they are 2, but I'm going to make them 3. Sorry about that. I think I meant to do that because that would make this a way more complicated problem. So we need to divide this, but can you take the cube root of 54 or 128? No. But you can simplify them by simplifying radicals, which that's pretty much the third step, but you have to do it in this problem anyways. So for 54, what you're basically trying to do is think of how you can split up 54, and then think of two numbers that multiply to equal 54, and one of them you can take the cube root of and get an even number. So let's see, we could do not 18 and 3, 27 and 2. We could do that because you can take the cube root of 27. Well, actually, I'll just put that over here. 27 times 2. And for the x to the 5th, that can be taken out. And here's what you have to do. You have to split up the exponent into two things that can be added. One of them can be divided by 3. Because how you can get an x out is by dividing it by 3, because that's the index. So we can see that we have x, and if we split the 5 exponent into two things that are added, and one of them can be divided by 3, we can do 3 plus 2. Because 3 plus 2 is 5, but you can take the cube root of 3. Yes, you can. Or, well, sorry, that's not what I meant to say. You can't take the cube root of 3 and get an even number. I meant divide by 3. You divide it by 3 because of the index. Sorry, I was getting mixed up. So we have that. And we will be able to simplify some things afterwards. So that's the top. The bottom, 128. What two things can multiply to equal 28? One of them you can take the cube root of and get an even number. That would be 64 and 2. And then x cubed, we don't have to split that exponent because 3, the exponent, can already be divided by 3. So now we take away things that you can take the cube root of and get a number evenly. Well, also, I forgot to say, there's a rule, when you have two things that take the cube root of, you can just put the radical symbol over the full thing. So we can just do that. So I'm going to highlight things that we can take the cube root of and get something evenly. Or you can divide by the index. So that would be this. Okay. So now we have 27. The cube root of 27 is 3. And then we, on the bottom here, the cube root of 64 is 4. So we have 3/4. Now we have the x cubed and the x cubed. And what you do is you divide this by the index. So 3 divided by 3 is 1. So just x. And then on the bottom also x. Then we have that multiplied by the cubed root of something. Let's see. What do we still have? We have 2 divided by 2. And then on top we still have this 2 here, and that's an exponent. So we have to do x squared. So basically, think about how this works. We have these 3 x's, in case this didn't make sense. So we have x, and we have x squared. What did we do? We took the cube root of them. So to get back to the normal of what we had, we would have a 3 and a 3. And this was on the top. And if you multiply these, you would get x to the 5th, and you would still have x in the 3rd on the bottom, which was what our original thing was. So hopefully that makes sense of how I got that. So now... Oh, didn't mean to do that. To draw. The x's can cancel out and the 2's can cancel out. So we have 3/4 times the cube root of x squared. And that's as simple as it can get. Unless you happen to want to do x to the 2/3, but we're not getting into that yet. That's the next lesson. So this would be our final answer. And these cancel out because they're anything that's the same on the numerator or denominator. You can do that. Okay, that's multiplying and dividing. Now simplifying, which that pretty much was simplifying. But just to reiterate, this forgot to put a closing parenthesis on that, sorry. Steps, these are not really in order, they're just the can-dos, and there's not necessarily rules for this. So these are just things you can do, they're not really steps. So you first need to add, subtract, multiply, and divide when possible. Then you need to take, you can, if possible, take of variables. I don't know what I was trying to say. I think I was trying to say take out variables. Yeah, that's what that's supposed to be. Out. Take out variables by splitting apart x. I don't even know. I didn't splitting apart exponent. That's not even correct English. Sorry about that. To make them divisible, factor, divide, but the index by. That's what we did up here when we were doing the x. Remember, we split apart this right here and made it 3 plus 2 because the 3 you can take the cube root of, or you can divide by 3, which was the index. And then you can rationalize the denominator, which I haven't shown you yet, but I'll show you an example. So, to review of taking out variable, we need to see if 448, if you can, if you're able to split that apart. So let's see, what two things can multiply to equal negative 448, and you can take the cube root of one of them. So that's kind of hard to think of. But that's certain numbers that you can take the cube root of are, we know that you can do that with 8, so can 448 divided by 8 to get 56, yes. That might not be the most even one, so let's keep looking. What about 448 divided by 64? Oh, that does work. 7, okay. Alright, so 64 and 7. Let's just make the 64 negative, because it has to be negative 448. So we know that. And then x to 17th. We need to split that up. Oh my gosh. So that the exponents have something that can divide by 3. So 17 can't divide by 3 evenly, so that's why we need to do that. We can do 15 plus 2. That equals 17, and you can divide 15 by 3 and get even number. And then for the y, we can do 3 plus 1, because this can be divided evenly. So that's what that is. Now we can take the cube root of things that we're able to, which is negative 64, x to the 15th, and the y cubed. We can take those out. We would get negative 4 out here. X to the 15th divided by 3 is x to the 5th, and x cubed divided by 3 is just y. Or sorry, I meant to say y. Y cubed divided by 3, that would be just y. And then we still have things under here. We have a 7 left over. We have an x squared left over. And we have a y to the first, or just y. So that's what that would be. Okay, rationalizing a denominator. What does this mean? When we rationalize, we need to multiply the denominator by itself so that it can become a perfect square, because we can't have the radical in the denominator. That's just a common rule, and that will make it further simplified. But we don't need to do that yet. We can change this to this. That's one rule we know. We can just do this. And we know 10 over 6, that it simplifies to 5/3. Now, we need to rationalize the denominator. This isn't technically the most simplified answer. And we can do that by multiplying the denominator by itself. It will then become a perfect square. Well, actually, depending on whatever the index was, if there was a 3 here, you would want to do 3 times 3 times 3. But we're not doing that. And then you multiply the numerator by 3 as well. Then we get 15 divided by 9. And we now see that we can take the square root of that. And we have 3 on the bottom and root 15 on the top. Or we really could we could bring out the 3 if we wanted to, like this. Well, since it was on the denominator, it would have to stay on the denominator. We would have 1/3 times that. We don't need to do that. That's more complicated. So basically, you take the square root of that, you get 3, and then root 15 on top. That's rationalizing denominator. Okay, then we have one more, a full example. Well, this is really just the same as before, but now we have a different root here. So we need to see if there's something that 625 can divide by, that you can take the 4th root of. Let's see if there is something. Well, let me think. So let's see here. 25 and 25, you could do that. And wait a second. 625. Oh yeah, that is a perfect one. Never mind. I was getting confused. That's a perfect one already. You don't even have to do anything to that by simplifying it. All right, the m and n, we need to split up the exponents so that something can divide by 4. So we can do 16 plus 5 for this one. And then for the n, we can do 4 plus 1. Because we see the 16 and 4, they can divide by 4 evenly. So we have not squared. 4th root of 625 is 5. The m to 16th. The reason why we're doing this, we're dividing, is because when you that's what happens. Like the exponent rules, I'll go over them at the end of the video again, just to reiterate it. Well, actually, that will be on the next video, but I'll do a brief thing. So, hang on a second. So, we have the m to the 16th. We divide that by 4, and we get m to the 4th. Then, n to the 4th divided by 4 is just n. No number left in there. We just have n to the 5th. M to the 5th. And n to the 1st. Oh, that actually wasn't the best decision, because still this isn't simplified. We further can make this m 4 and 1, and then we have another m out, which would mean m to the 5th, actually. And then we have mn in here. What I could have done instead of 16 plus 5 is 20 plus 1. I wasn't thinking of the most possible thing. Basically, if you end up with a number on an exponent in here that's greater than the index, then that means that it can be further simplified. So we need to have 4 there. Just I'll make this further away so you don't think that's n to the 4th. Okay. That's our answer. So let's review some exponent rules real quick. Talk about them more. So when you have, let's say, a times b, and you have exponents c and d. Well, we can just put them in here, c and d. Well, that's not a good thing to do. Dang it. So I'll just use actual numbers. So we know that not plus times. I'm not doing a good example at all. Sorry. Let's keep. Now we have it. Okay. When you're multiplying the bases, the exponents add. Okay. When you divide the bases, the exponents subtract. So we see we had 2 plus 3 equals 5. We have 3 minus 2 equals 1. And when you have something like this, where we have x, when you are doing an exponent of the base, you multiply the exponents. And when you're doing the square root of a base, you divide the exponents. So see how that works. Here's a case where you add them, where you subtract them, where you multiply them, where you divide them. That's what you're doing with the exponents. But for the bases, you are multiplying, dividing, doing an exponent of, and taking a root of. It doesn't matter. It might not be square root. It could be anything like that. So you see how these factors are related. Some make a number larger, some make a number smaller, but regardless, those are the cases when you do operations. And that's our next lesson. So thank you for watching, and that'll be it.